You can see here it says use the Biot-Savart law to calculate the magnetic field at the point indicated. Note, the point and the wire and the current all lie in the two-dimensional plane of the page. So this is a very simple application of the law of Biot-Savart. It's potentially nasty because you've got to do three parts, but ultimately we'll get a result that we can use and make some sense of what we found in the in the second example and the third example. So, in other words, this is going to help us to do another problem just like this. So, what we have here is a current carrying wire that enters straightly from the left-hand side, then makes a arc of radius r, and then exits straight upward. So I didn't actually label the radius r, but that's basically the dimension. In order to do this problem, we're going to have to use the law of Biot-Savart. So I'm going to refer to solution again. And the solution is that the differential bit of magnetic field dB is equal to mu 0 I over 4 pi times dl cross rp minus rdl divided by the magnitude of rp minus rdl to the third power. Now, the dl is a differential line segment vector that points along the current carrying wire in the direction of the current I. RP is a vector that points from the coordinate origin, whatever coordinate you choose, from the coordinate origin to the point P at which we wish to know the magnetic field. The vector RDL points from the coordinate origin to the location of the differential length vector DL. And then, of course, RP minus RDL magnitude is just the magnitude of that vector. So this is what we're going to use. One thing we did discover earlier is that a whole circle gave us basically B magnitude was equal to mu 0 I. I'm going to write this in a somewhat weird way. I'm going to write it as 4 pi R. And then I'm going to put delta theta, or actually, let's do it this way. Since I'm trying to just express exactly what the uh, relationship is to the magnetic field strength and to the angle that the arc turns through, I'm just going to put 2 pi like this, and that gave us a idea of what we could do for any arc, as long as we were trying to calculate the the magnetic field in the same plane as the arc and at the center of the curvature for the arc. Then the magnitude is going to be mu 0 I over 4 pi r times whatever the angular measure is. For instance, in this example that I'm getting ready to work, you can see the angular measure is only basically pi over 2. So we could actually call that little part in parentheses, we could call that pi over 2. A whole circular arc of radius capital R would have a magnetic field strength in the same plane as the arc and at the center of curvature of the arc, given by mu 0 I over 4 pi R times the angle that the arc goes through, which in the case of a full circle is 2 pi, whereas in this it's a quarter circle, so it should actually be pi over 2. So hopefully that'll come into play and we'll be able to make use of it in a more robust way as we go on. So now we can begin. I'm going to go ahead and draw a coordinate system so we can make some sense of what RP and RDL are. In fact, I think it would be very smart to call the y-axis the vertical axis going right through the point P, and I'll call the x-axis the horizontal axis pointing to the right, like so. So now that you can see that the point P is really at the origin, then we have the wonderful idea that the resulting RP vector is just equal to the zero vector, because obviously the vector RP is supposed to point from the origin to the point at which we wish to know the magnetic field. By me putting the origin at the point P, I've made the RP into zero. Now I've also got to break it up into three parts. I'm going to label this part 1, this part 2, and this part 3, and we're going to work out exactly what RP, RDL, and DL are in each of those cases. Now, if you've actually taken the time to look at my example 1 and example 2, you probably already have some sense of how to go about calculating DL. I will draw them here and not put as much work into it as I have their other examples. So for part 1, I'm going to have a DL vector that points this way. So I'll call this DL1 for DL part 1. For part 2, I'm going to have a DL vector that is shown there. This is DL part 2. And then for part 3, I'm going to have a DL vector, DL3. And we can go ahead and work out what those are. So for starters, let's take part 1. DL obviously points in the X direction because the current's going to the right, and DL is supposed to point in the same direction as the current. So in part 1, the current's going to the right, and the right is the positive X direction. So we can go ahead and say that DL, which I'll switch to blue. Now I'll go ahead and stick it to purple because that's what we've been doing on the previous ones. DL part 1 is going to be, in this case, since I've laid the DL parallel to an x-axis, it might as well be called dx instead of DL as the length. And then, of course, it points in the positive x direction, so I'm going to put an I hat with it, and that's the DL. The RP, of course, we already found is 0, but the RDL in this case, that's going to be a vector that points from the origin to the DL. I think you can see that that'll be some x coordinate long, specifically in this case a negative x coordinate long, and it points in the negative x direction. So I'm just going to write negative x I hat. The negative indicating that it points to the left, the I hat indicating that it points right or left, but I being the positive and therefore right direction, and X being the length of the vector, which would obviously go from some bigger number down to basically R, because as I said, the radius of the circle is supposed to be R. I didn't write it on the diagram, but we're going to keep on going with it. Actually, I should go ahead and take the time to write it on the diagram, so I'm going to do that now and just say that this distance is R, and of course, so is this distance is R. So we're using capital R for that. I now have that for part 1, and now I can say for part 1, I can calculate DL cross R, because this ultimately is what causes this problem to become somewhat trivial. So again, continuing for part 1, I have DL cross RP minus RDL. I need to compute that. So continuing on in terms of part 1, I'm going to say dx I hat cross. Now RP we said was 0, and RDL we said was minus x I hat. So 0 minus x r hat would be positive x. Oh, I said r hat. X I hat. So when we take the cross product of those two, this becomes x dx I hat cross I hat. But of course, I hat cross I hat is just 0. And that's because, again, you get the A cross B has a magnitude of A times the magnitude of B times the sine of the angle between them. These two are obviously parallel, so the angle between them is actually, I don't know why I wrote theta, it's actually 0 degrees. And that, of course, is 0. So we can see already that 1 does not contribute. So we're saying it does not contribute to the magnetic field B. Now we can do part 3. Again, I'm going out of order for a good reason. So for part 3, I am going to say that part 3 we have dl. Notice this time dl is pointing in the positive y-hat direction, or in the positive y direction, which would be in the j-hat or the y-hat direction. And again, the dl, since it happens to be along the y-axis, why not call it dy? So this is going to be dl is equal to dy j-hat. Similarly, we already know RP is equal to 0, so RDL is supposed to point from the origin to RDL. Obviously, RDL doesn't start till we get to a Y value of R or larger, just like before it only ran up to a X value of negative R. This time it actually starts at a Y value of positive R, but it is along the y-axis, so we might as well use the y-coordinate to indicate its direction. So I'm going to say RDL is actually equal to y, and then it points in the y direction, positive y direction, which is the j-hat direction. Therefore, we can see that RP minus RDL is going to be just, well, we'll do that in a second, but I'll go ahead and compute the DL cross uh, DL cross RP minus RDL. The DL is obviously going to be dy j hat, and then we're going to cross that with RP minus RDL. RP is 0, so RP minus RDL is going to be negative y j hat. When we take the cross product, we get negative dy, negative y dy. I'll go ahead and take another line. I don't want to try to fit it in there. We get negative y dy, and then j hat cross j hat, which again should be equal to 0 because it's 1 times 1 times sine of 0. So again, we see therefore 3 does not contribute to be the magnetic field. And in general, what you can see is anytime you have a DL vector that is running parallel or anti-parallel to RP minus RDL, then you're automatically going to get 0. And that's just true for because of cross products. So whenever you have these radially propagating currents that are radially propagating towards or away from a point at which you wish to know the magnetic field, those radial vector or those radial current parts are not going to contribute to the magnetic field. And this brings us now to part 2. And part 2 is a little more straightforward. We've already worked out the details of what DL would be. This is obviously DL's part of a little arc on a circle of radius r. So I'm going to go ahead and say that DL is actually equal to, and this is specifically DL2. DL2 is specifically, oh, and I should have written 3 on that one as well, and I didn't. I didn't write it on. I didn't write 1 on this one, and I didn't write 3 on this one either. But anyways, DL2 is going to be RD d theta. Now, again, we're going to have to work out exactly what this detail is as far as the direction of the vector goes, but the direction of the vector can be treated this way. I will go ahead and switch to black, and what we're going to notice is we'll have a x-axis, we'll have a y-axis, and then what we have here is a dl vector that is somewhat perpendicular. Let me show it to you with a green vector. So we're going to draw a green vector that points out this way, and then another one that points this way that's just a line. I'm going to say this is the angle theta, this is the angle d theta, and again we can get another system or part of a coordinate system right at this particular dot by imagining our x-axis is that way and imagining our y-axis is that way, and realizing that our vector that we actually want is in fact this guy. So this is our dl vector, and with that in mind, we can see, for instance, that this angle is theta, and therefore this angle is also theta. Excuse me, I made that way too small. So this angle right here is theta, and this angle right here is also theta, so that we can see, for instance, the x component is in fact positive, so that's dl sub x, and the y component is positive as well. And in fact, we can see that the x component should be positive dl cosine, or excuse me, positive dl sine theta, and the y component should be positive dl cosine theta. So now I can go ahead and say that this result should be, let me rewrite this a little lower because it's clear that I'm running into my own diagram. I'm going to say dl, supposed to be dl2, is equal to r d theta, and then of course, as we said, the x component is positive sine theta, so I'm going to say sine theta I hat, and then the y component, of course, you have to take dl, which is the magnitude of dl, which is rd theta times sine theta to get the y component. Similarly, or excuse me, get the x component. Similarly, to take the y component, you have to take the magnitude of dl, which is dl or rd theta, times the cosine of theta. So this is going to be plus cosine theta j hat. So that's what our dl vector is in this particular case. And in fact, for our right-hand rule, we might want to realize that if I grab dl2, my thumb pointing in the direction of the current like this, then I see that my magnetic field goes into the page this time, and the way I have x and y drawn, that would be the negative k hat direction. So that's something to keep in mind, so that if we do the calculation and come up with a result that contradicts that, we need to check our calculus, or we need to recheck our way of coming up with the right hand rule telling us it was going into the board, or with the fact that going into the board was in the negative k hat direction or the negative z direction. So anyways, that's our DL2. We've got that. Now I also need my RDL, and that's just a radial vector pointing outward. In fact, it looks a lot like this guy right here. That's my RDL. And you can see that has a x component that is just r times cosine theta, and it's got a y component that's r times sine theta. And in both cases, of course, they're positive. So now I can say r dl is equal to the magnitude is r, because remember this green line that I have here is drawn from the origin to a point on the wire, so that this distance right here, that distance is r. So that distance is r. So r dl should be r, and again cosine theta. Whoa, might help if I write with a pencil. R cosine theta I hat plus r sine theta. Ooh, and actually the x component should be negative. My fault. I should put a negative sign in there. And the y component should be positive, and that's r sine theta j hat. In this case, as always, RP is equal to 0, so we can go ahead and compute dl cross RP minus RDL. So dl cross RP minus RDL is actually equal to R cosine theta. I'll leave the d theta out in front. So I'm going to first write this like this. I'm going to say d theta, and then I'm going to say R sine theta I hat plus R cosine theta j hat. That's going to be crossed with RP minus RDL, but RP is 0, so when I go RP minus RDL, that becomes minus a negative R cosine theta. So that's plus R cosine theta I hat, and then 0 minus R sine theta j hat. Now we can do the cross product with this, again using FOIL, first, outer, inner, last. The first is R times R times sine theta times cosine theta. So all of this is, of course, going to be r squared times d theta. So I'm going to go ahead and factor all that out. Now I'm going to get square bracket. This is going to become sine theta cosine theta I hat cross I hat, which is obviously 0. And then we do our outers. That's the first with the last. So r times negative r. We already got the r squared, but this is minus sine squared theta I hat cross j hat. And now we're going to do the inners, and that's r squared times cosine squared theta times j hat cross I hat. So we've already got the r squared, so this is plus cosine squared theta j hat cross I hat. And then the last is r squared times sine theta cosine theta times negative in this case. So this will be negative, oops, this will be negative sine theta cosine theta. And again, we've run out of room, but this one is j hat cross j hat, which is, of course, 0. So we got a 0 here. We got a 0 here. Using your right hand rule, you can see I hat cross j hat is k hat. So this one becomes k hat. And j hat cross I hat, being the opposite of I hat cross j hat, is negative k hat. Which is good because we already had a negative with the k hat one, and we didn't have a negative with the cosine squared one. But now that we have j hat cross I hat is negative k, now they're both negative, which means we can actually get sine squared plus cosine squared equals 1, and that makes our simplification a lot easier. So what we're going to have now is r squared d theta times parentheses sine squared theta plus cosine squared theta times k hat with a negative out in front. Uh, Let me go ahead and put the negative out in front by moving this equal symbol. So there it is, and we are getting, based on this, we are getting that the coordinate direction is in fact in the negative k hat direction, which is exactly what we predicted with the right hand rule. So now finally I can write that b, which equals the integral of db, and that's over parts 1 and 2 and 3, but we got 0 for part 1 and 0 for part 3, so all we have left now is just what we got for part 2. So this is going to become, pulling the constants out in front, negative mu 0 I r squared over 4 pi times, now I've got to take the integral of dl cross rp minus rdl, which we already found was just r squared d theta. So this is going to be d theta, and this is in the k hat direction. And then all of that divided by the magnitude of rp minus rdl, which you can see just like we did in the last example. If you take rdl and realize that rp minus rdl is essentially just the negative of that, you're going to get that capital R is the magnitude, and since it's cubed, we have to put capital R cubed down in the bottom. You can see that that cube cancels out with this 2 up here. And now we're going to get that negative mu 0 I over 4 pi r k hat times the derivative of cosine, or derivative of theta, from theta equals 0 to pi over 2 in this case. So I'm going to just say it's pi over 2, and you can see that that actually causes us to lose the pi, but we gain an 8 in the bottom, so that now we can say b is equal to negative mu 0 I over 8 r k hat. And that's the entire answer. And just again, putting this in terms of what we already know, so that formula fits with this figure. Again, you just have to use the right hand rule to decide whether it's in the plane or out of the plane. Hope that helps. Have a good day.